Taking the volumes of revolution. I hope you enjoyed today's lesson. It's the last one in calculus. Our last topic in calculus is volumes of revolution, or solids of revolution. It says here that a solid of revolution is formed by revolving a plane region about a line. We're going to use the x and y axis. Here are some examples of revolving a plane region around the y-axis. If I got a plane, say this is a line 2x plus 7. I've got a positive slope. And between the y-axis and the x-axis, I've trapped a plane region in 2 dimensions. Now let's revolve that. Think of picking this up and revolving it like a helicopter blade around the y-axis. Well, if we did that, if we revolved it very quickly, if I took the y-axis like a stick and I kept on twisting it very quickly, you'd get a plane figure like this. It would come out of the board and then go back into the board and look almost like a cone. With this curve here, y equals x squared, I've cordoned off a plane region here. Again, if I grab the y-axis and turned it like a stick very, very quickly, like a helicopter blade, we'd see this plane region would go to here and would be kind of coming out of the board and going into the board, almost like a bowl that you could fill with Fruit Loops and eat on a Saturday morning. Well, what kind of problem do we have to worry about here? Our only worry is problems where we are rotating about the x-axis. So I have some curve here, y is equal to f of x. I grab a hold of the x-axis and I spin this curve around and around and around, and eventually I'll get a solid figure like this. And if I want to evaluate, well, what is the volume of this in 3 dimensions from A to B? Well, I'm going to get a curve that looks something like this. Something roughly like this. And if this is my starting point and this is my ending point, I have to know that from the x-axis up to my curve is going to be a distance of f of x. That's like the radius of this circle here. And instead of taking little rectangles as we did in 2 dimensions to find the area under the curve, we are going to we're going to slice discs away. So I've sliced one disc here, and it looks something like this. This is like cutting the ham at Christmas. You cut a slice of ham off. And what does that slice of ham look like? Well, if I take one slice of ham out, I have a radius of f of x. And the thickness of each of these is going to be called dx. Just as the width of our rectangle in 2 dimensions was dx, the thickness of each one of these discs is dx. Well, let's consider, what does the volume of a can of cola or Coca-Cola look like? Well, our volume was whatever the area of the end was, which was, it's a circle, so it's pi r squared, times whatever the height of our can was. So the volume of a cylinder there is this, pi r squared h. Well, we're going to use the same type of reasoning here. We're going to integrate from a to b. We're integrating from a to b of, well, let's consider the area of the end here. The area of the end here is pi r squared. Well, what is our radius? We know our radius is f of x. So it's going to be pi r squared, but instead of r, we're going to have f of x, because that represents the radius. Squared. The biggest problem I see is a lot of people forget to square that. Well, that's your radius squared. Well, we're taking the sum of all of these little slices. What's the width of each slice? Instead of taking the height of the whole thing, we're going to take the sum of the widths. What's the width of each little slice? Well, we found that that's dx. So here is what you need to remember, is that we're going to integrate from a to b of pi r squared, well, r is f of x, pi f of x squared, and dx is the width of each of those little slices. These little slices, or these little slices, we're going to be adding them up. So we're taking the limit as the number of slices goes towards infinity. Or alternatively, you could think the limit as dx goes to infinitely small, or to 0. Let's do an example of these solids of revolution to see what we're talking about here. The curve y equals the square root of x minus 1 from 1 to 5 is rotated about the x-axis. So I'm going to grab this x-axis and spin it. It says sketch the solid and find its volume. Well, the first step is I have to sketch the solid. I know it starts at 1, and if I plug in a 5, I get 2. I get plus or minus 2, but for now we'll take the principal root. So this is what it looks like, a one-armed bandit. I call these the one-armed bandits, these square root functions. Well, if I rotate that around, obviously it's going to go through 5, negative 2. So down here at 5, negative 2, I'll get my second point, and I'm going to have something, if I'm just considering this part here, so I can erase that, and I can erase that. If I'm rotating this solid, I'll get something that looks like this. And it'll be a nice 3D solid of revolution. Now, if I'm slicing, each one of these slices is dx. And each of these radii is f of x. Notice, the radius changes as the x value changes. Here, my radius is a lot smaller than it was there. The radius changes. It is f of x, the function value at each x value. Well, how do I find volumes of revolution? I've got to integrate from 1 to 5 of pi f of x squared dx. I can pull the pi out from 1 to 5 of, well, what is f of x? It's x minus 1 to the 1/2, and I'm going to square that and take that with respect to dx. I pulled my constant pi out. Well, if I square the 1/2, if I multiply, it's power over power, so I multiply, I'll ultimately get pi from 1 to 5 of x minus 1 dx. I've just multiplied 2 times 1/2. Now you have to know how to integrate that. You'll get pi times x squared divided by 2 minus x, and I'm going to evaluate this from 1 to 5. When I do this out, I'll eventually get, if I plug the 5 in there, minus, and I plug the 1 in there, I get pi times the values 13 minus 5. And ultimately, this is going to leave it as an answer to 8 pi. 8 pi, what kind of units do we have? Cubic units, because we're talking about volumes.